Okay, what's the first question we ask? Chain, right? Chain. Undoing the chain rule. So that should be e to the x down there. Okay, there we go. Is it undoing the chain rule? So what would be one small change you could make to this so it would be undoing the chain rule? What could be one small change you could make? In this case, not adding something, but just removing something. What could you remove, and then it would be undoing the chain rule? One of them, or a specific one? What if I removed that? Would it be undoing the chain rule? You should see yes. That would be, now it would be undoing the chain rule if I remove that. Because what? Because e to the 2x is the derivative, essentially, of e to the 2x. And this whole thing is to the negative 1. So our first attempt would be? Yeah, what would the first attempt be at the antiderivative? Natural log of this denominator, right? Because this is to the minus 1, and there's the derivative of the interior, e to the 2x, the derivative of that. So the problem now, the problem I gave you is this part of this interior function is derivative of that is not up there. So another possible thing could be that would be another, let's see, no, that wouldn't work. That wouldn't work because of the 2. So anyway, let's just go on. I don't want to spend too much time on that, but it's not undoing the chain rule, okay? So we go through our other things. Is it one of the common forms for undoing the product rule? Definitely not. Is it partial fractions? Is it one polynomial divided by another? Sort of. Sort of. It sort of is, right? What polynomial is this like? So this kind of looks like what set of polynomials? It's kind of like, isn't it kind of like x squared over x squared plus 3x plus 2, isn't it? Yeah. But instead of x's, we have e to the x's, right? So that's where we can, this is what this idea of changing the variables, making a substitution to solve this. If I say let u equal e to the x, okay, then this would really be what? This would really be u squared, right? E to the x to the power 2. So with that, and this would be 3 times u. Now, we'd also need to know what dx is. So we can say du, what's the rate of change of e to the x? E to the x. And what does that rate of change mean? It means given any small change in x, change in u is e to the x times that change in x. So that's our dy equals mdx. And this allows us to solve for dx. So if I'm going to change this into a different variable u, then everything that has an x in it has to be substituted. So I'm doing this because I need to know what dx is. So what is dx? Dx is du over e to the x. But what's e to the x? U. So what I'm seeing here that this is like partial fractions, but like partial fractions where the polynomials are of e to the x, not x. And so by doing this change of variables to u, I can make it a true polynomial over another polynomial. So this is going to be the same as e to the x is, or e to the 2x is u squared plus 3. And then we found out what dx was. We did the math here, And we got dx was 2u over u. Notice dx is not just du. It depends on how we choose u in the beginning that tells us what dx is. So you got to chase out the algebra, chase out the math. Dx is du over u. Okay, what can I do now? Yeah, I got u squared in the top and u in the denominator, so and what if there wasn't any u's here up in the numerator? What would happen to this u? Just multiply by the denominator, right? So this is just a fraction times a fraction. So it's not, you're not going to, every problem is not going to fit this exact cookie mold of this problem. You got to just do the right algebra. Just you follow the math, right? If there's no u's up here, you can't cancel the u, and the u multiplies to the denominator. Make sense? All right, now what do we do? Yep, so we can rewrite this as? So only if this factors. Does this factor? Yes. U plus 1, u plus 2. Okay, so now we're on partial fractions, which we've done before. So any questions on what I did to get there, right? So all this stuff, changing all the x's into u's according to this setup here. Anybody have a question? Does it make sense? Okay, and so then we have, a times u plus 2. I'll do this fast. This is an easy one. Plus b times u plus 1 equals to what? That's my numerator. Has to equal u, right? This u right here. And that's u plus 0. So my coefficient of u is 1, so a plus b has to be 1, and 2a plus b has to be 0. Subtracting, minus a is 1, so a is negative 1, b is positive 2, and so then this thing is okay, and so then I'm ready to take the antiderivative, which is negative natural log of u plus 1 plus 2 times. Okay, is that the answer? Yeah, so our problem was not in terms of u, it's in terms of x. So then we can change it back, right? So we changed it into this new variable u to be able to do the antiderivative. We do the antiderivative, then we got to change it back to get the actual closed form of the original function we were given. So it will be negative ln of e to the x plus 1 plus 2 ln of e to the x plus 2. Okay, did I lose you or did I make a mistake? Did I do everything right? Anybody have a question? So you can change the variable, this thing we call u-substitution, which one application of that technique is you've got another technique that we can use, but we need to get it, like this could be like if this were e's or cosines or sines, and by changing the variable, you kind of remove that composition and you're left with a more simpler one, something we've done before, in this case partial fractions. Yes, please. It would if it didn't cancel out with one of these. That's what had happened here. Because there's a u squared now, that u squared over u is this u here. But you're absolutely right. If there was no u to cancel out with one up here, then it multiplies into the denominator. Yep, it's part of the math, right? This is part of the math. Other questions? Good, can I erase it? Okay, another example. First question we ask. Is it undoing the chain? No, it's not. What small change could we make so that it would be undoing the chain? Tell the person next to you. What's one small change you could make to this so that it would be undoing the chain rule? Tell the person next to you.
Because they're going to just get x minus e to the 3 halves. Or 1/3, excuse me. 1/3.
Okay, what change can we make? X squared, this one x squared? X squared here? Yeah. Have you any confidence? X squared here? No, right, no. So what do I want? X squared here, right? That makes it undoing the chain rule, correct? First attempt is? First attempt, if this were the problem? We're experts by now of undoing the chain rule, right? First attempt would be? X squared minus 8 to the? This is 1/3 power. 4/3, right? And then we need 3/4. And we'd also need 1/2. Are we becoming experts at that? That was the goal from the beginning. Hopefully we're becoming experts. That if you couldn't do that, that you followed, you were like just a hair behind me when I was doing it, and you follow it completely. If not, time to hit the books. All right, but we don't have that. We have this one. So here's another example where I can do a u-substitution or change the variable to help us. So what will I let u and be? Yeah. What do you think? Yeah, so what's when you have square roots and cube roots and things like that, what locks those things in is like you can't multiply is when you have sum or difference. So by doing u equals x minus 8, we get rid of the difference of two terms and we just make it one term. That's easier to work with, right? If you have the cube root of one thing, that has the ability to multiply and do other things. But this x and this x minus 8 is kind of locked under that square root or that cube root. So that's limiting, right? So by making all one term under there, that can maybe free us up. So we'll see what happens. So what is du here? Du equals 1 dx. Now in this case, dx is du. You can just replace the dx with du, but that doesn't always happen, as we saw in the previous example. Okay, and then we need to know what x is. So we know u is x minus 8. What is x? Was it? U plus 8, right? If you just solve this for x, add 8 to both sides. So now we get everything we need. We're going to the integral of x is u plus 8, that's x, times cube root of u, and then dx is, in this case, just du. Did it help? Did that help? Can we make some progress now, where we couldn't before? What can we do? Yeah.
What you can do is you can make the cube root of u into u to the 1/3.
That's right.
And then you can distribute it to your u plus 8.
Right. So now u the 1/3 we can distribute into the u plus 8, and we just have two easy terms. So it'll be u to the 4/3 and 8u to the 1/3. See what happened? Now it's easy. Power rule, right? Power rule gives us, what is that, 3/7 u to the 7/3 plus 8 times 3/4 x to the 4/3. Did I do that right? Oops, u. Okay, and then what now? Are we done? U is the same as x minus 8. Easy simplification here. That makes 6. 3/4 of 8 is 6. Okay, so I want you to tell the person next to you, what is the meaning of that expression right there? What does it mean? What does it do, or what does it mean? Go. Everyone's talking to somebody. What's the meaning of this? Okay. Let's see here. Oren, what do you think? This is he said the accumulation function whose rate is this one? What do you think? The accumulation function? Close, okay. The closed form accumulation function? The total net accumulation function? What's that?
It's the whole family of.
It's lots of them, right?
Yeah.
Which ones is it? All of them. Why is there more than one? Why is there more than one? Right, but why is there a plus c there? Why is there more than one? Why is there... Right. So we can start at any x value a. And depending on the x value a we start at, we get a different net accumulation function. Right? So this is all net accumulation functions that have this rate of change. And by all, we mean starting from any x value a. Right? Starting from any x value a. And this plus c accounts for that, right? Adding a constant accounts for starting at any value a. Okay, so if you were to, let's say this was definite, like we're starting from 3, and then we wanted the value of the function at 7. Okay, so I'm going to let my a value be 3, and I'm going to start from 3, and I want to know the accumulation as we accumulate from x equals 3 to 7. Okay? So how do we do that? There's two possibilities. I can come back to this, right? I can come back to my and what would I do with this? What would I do to evaluate from 3 to 7? Right, so we're going to put in 7 and 3 and subtract, right? So it's final minus initial. The final value of the net accumulation minus the initial. Put in 7, put in 3, and subtract. But there's something else we could have done. I could have done that here, too. But would I go from 3 to 7? Yeah, right? So when x is 3, what is u? -5, right? And when x is 7, -1. So I could just stick with this one, not substitute back for x, but then evaluate from -5 to -1. Yeah, so it's just two different ways to approach this. You can, if you have a definite integral, you can just keep it in u and then change your bounds into u's. Or you can switch it back into x and use your x bounds that were given. Okay, so those will be the same. Does that make sense? Okay, I'll give you 3 practice problems here. I'll take attendance and we'll see how we do. Questions before I erase this? Anybody have a question? So yeah, so in the exam, it's possible that you're free to do anything you want, or I could specify, use this technique. So either way is possible. Does that answer it? I don't remember. I don't think you do. But I have to check that today.
So if we don't want the x to like actually calculate the number.
It'll be fair. If you don't have a calculator, it'll be fair. Okay, see you doing these.
It is long, but you mentioned it. What about your
Probably.
Oh,
What did I
you
say? Oh, right. So dx is right.
Okay, so we could rewrite here, right? We get here, here. Here we get here. Because you have to distribute u to the 19. Oh yeah, you could do that, but I did it like here and then I separated it. No, they're not. They're not plus. That's the thing, though. This
Is that what you got, Nick?
This is a multiplication.
I'm just saying.
So you have to multiply. You can't only take two separate intervals if it's additive. It's like the addition and product. Yeah.
Yeah, that's what I got.
Yeah. Okay, look at those first two. See if you agree with those, or
And I think the first one's the same basic idea. Yeah. Okay,
any
so-
questions on the first two? Yes, please.
I'm a little confused. So the du equals 1/2 dx.
Uh-huh.
correct?
Uh-huh.
And then you have du at the end. What would you do after that to make sure, yeah, for the first one, so that you take into account that it's 1/2 dx?
I did that here. So
Okay,
dx is then 2. So we need to find what dx is.
yeah.
So dx is 2 du.
Okay.
So my 2 is there. So here. Sorry. So I should have started this like that. And then I moved the 2 out in front. Is that better? Okay. Yeah, I just forgot to write it in that first step. Thank you. Any questions on the first two? So now the question is, how do we start this last one? So first of all, it's not undoing the chain rule. Why? Because sine x is not the derivative of cosine squared, right? It's the derivative of cosine, but not cosine squared. That's different. So you can't do undoing the chain rule here. So what we can do is to kind of get rid of that cosine squared. We can let u equal cosine. Then du is negative sine x dx. Now, notice something. What just happened? Do you see that du is what? Sine x dx, basically? And do you see right there what we have? So rather than solving for dx, which would have sine x in it, and we wouldn't know what to do, you can just notice that we have sine x dx in the problem. And we know what sine x dx is. What is sine x dx equal to? The opposite of du, right? The opposite of du. So this right here is equal to the opposite of du. Do you see it? If you solve for dx, then it'll have sine x in it, and we'll be stuck, right? Because we can't get this. How can we get the sine x in terms of u? U is cosine x. But if we notice that sine x dx is part of our problem, what does it equal? It equals the opposite of du. So then we'll have, just quickly here, so we'll have negative du over, or negative 1, over u squared plus 7. And then we did this about a week ago. We did something like this. Does anyone recognize this now? It's almost what? Arctan or arc cotangent, either one. But we got to make that a 1. And so you can look back, I think it was, what's today? Wednesday, last Friday or Wednesday I did something like this. You got to get that to be 1. And then you can use arctangent or arc cotangent. And you do that by multiplying top and bottom by 1/7.
guys want to study on Thursday or something? Or no? I mean, if they can't make it, I mean, yeah, sure.
The two you can
And this equals tangent. Five foot u over square root of 7. But then I need another times square root of 7. So -1 7 over 7. Tangent inverse of cosine x.
How do you get from u squared of 7 to u over radical 7 squared?
Because they're equal.
Great, why?
Because I need it to look like something over something squared plus 1. That's the arctangent.
Is this still equal?